motion in continuation. Earlier you are aware of that we are using the terms like omega for angular velocity in comparison to linear velocity v, and we are using theta angular displacement in comparison to linear displacement s or x. Same line, we are having one another term with you. A new term with you is that is torque, denoted by tau. It is a vector quantity. So this is the symbol for torque, tau. It is simply you have to place a line and a C you have to make like this. That's it. So this is how you have to make this symbol pronounced as tau, TAU. This is analog of force in the linear motions. When we talk about the translational motion, the term force which is playing the role, the same role is played by this term which is named as torque. So we call it as moment of force also. Like we are having inertia in the linear motion is are representative of mass of the body. More the mass, more the inertia. And that term in rotational motion, we call it as moment of inertia. So on the same basis, we are calling it as moment of force. The term with you is torque. And if I want to define torque, it is the turning effect of force. Turning effect of force, that is termed as torque. Like if I'm having this scale with me, I want to turn it. So I'm applying the force like this. So this hand I'm keeping fixed. This hand, my left hand, and on right hand I'm moving. So on the same basis, when you open the door, you are able to apply the force at its one end, and the door is rotating about the hinge. Hinge is fixed. This is the fixed point with you, and you are applying the force, and you have observed if I apply the force in the center, I have to apply more force. Handles are always provided at the corner because I'm increasing this distance, that is the perpendicular distance d with me. So this distance d is to be increased to get the more effective value of the torque, I can say. So the turning effect of force, that is termed as moment of force, or we can call it as torque. So this is a diagram to explain you that this is the hinge of the door if I'm having. Then I apply the force here at the one edge where the handle is provided, and this force is being applied here. And if this angle is 90, means perpendicular, I'm taking this line, then small d is taken as the perpendicular distance. And that can be taken as a lever arm also, scientific word with me. And otherwise d is the perpendicular distance from your axis of rotation to the point where you are applying the force. And this magnitude of the torque is given by the product of the force and the perpendicular distance. So if this distance I am decreasing, if this perpendicular distance I decrease, then of course I decrease the value of the torque. So it means for getting the maximum value of the torque for a given force, this perpendicular distance d should be having the maximum value. Now, if I want to write the units and dimensions for this new quantity with me, the physical quantity torque, which is of course a vector quantity, we are going to discuss in detail with you. But if I talk about its magnitude, I can give it by the product of the force and the perpendicular distance from the axis of rotation to the point of application of the force. Then this is given by the dimensions of force and dimension of distance, you know. So you are getting it mlt minus 2 into L means ml to t minus 2. So this is the dimensional formula for torque, of course same as work done, but it's a different quantity. You should be knowing this thing, that this is the disadvantage of dimensional formula, that for many quantities I am getting the same dimensional formula. So I'm not able to decide the physical quantity on the basis of the dimensional formula. But yes, if the physical quantity is given to you, you can be asked to find its dimensional formula, and that you should be able to do. Now, if I want to write its units, SI unit will be of course Newton meter, and if you want to write in CGS system, you will be writing it as dyne centimeter. Of course, as I've said, torque is a vector quantity. It is given by the product of R cross F, where R is the position vector of the point where you are applying the force. So I want to derive this formula for the torque in the vector form. This is my aim with me. I can say that I want to prove that torque it is given by R cross F. So I will be doing it into two parts. First part with you is I'm simply writing the formula for the torque in the Cartesian coordinates. In Cartesian coordinates when I'm dealing, then you can draw this diagram which is that this, if I'm moving from say point, if the diagram you want to make it more clear, then I'm taking this as the point, P point, where I'm applying the force, F force, and by applying the force I'm moving this point P to Q, which is clear from the second diagram. This is just to make you the values clear that what is R. So this is of course the origin. Now this is point P with me. This is the position vector R vector. I'm applying the force F. I'm moving this body from P point to Q point. Initially the angle for this position vector if I take, that is theta. And if I'm moving from P to Q, then the small angle which is moved is d theta. These all are my suppositions. Suppositions of course you are supposed to mention in the beginning. Now this is force is applied F. F is the force applied which is making an angle alpha with the x-axis. If I extend this line of the force, I'm joining it with the x-axis. This is making an angle alpha. And you are simply extending this line. Of course, you can write when I draw the projection on this your x-axis, this value will be equals to the horizontal component of R, that is R cos theta. And if you draw the perpendicular here on y-axis, this is your R sin theta. I'm doing in the component form. Here by using these relations, you can find the value of dx and dy, which I want to put in this expression. So when I take the derivative of x with respect to theta, dx by d theta, that is equals to r constant will be taken out, and for cos theta it is equals to minus of sin theta. So you can write this term dx equals to, because r sin theta is nothing but y. So you can write dx, it is equals to minus y d theta. Similarly, if you take the derivative of y with respect to theta, then you are getting it equals to dy by d theta, it is equals to r cos theta. So you can write the value of dy, which is coming out to be equals to x, because r cos theta is x, into d theta. So if you put these values of dx and dy in this expression of work done, then I can write it as, because fx is y d theta I'm taking it out, and for fy as it is, for dy it is x d theta. So I can rearrange it. I can write it as dw, it is equals to x fy minus y fx into d theta. So this was my aim. I was willing to write the work done in terms of the angular displacement. In place of dr, I am able to write it in terms of d theta. So this is angular displacement. When I am moving from P to Q, d theta is the angular displacement. So it means this term is playing the same role which the force is playing in linear motion. Like dw here in linear motion, I write f into dx. And or f into dr, if I am in 2 or 3 dimension, I will be writing it in component form. So this term x fy minus y fx is to be replaced by the analog term of the force in the rotational motion, which is torque. So I can write this dw, it is equals to torque into d theta. So this in Cartesian coordinates, if I write the value in terms of x and y, the value of torque can be written as x fy minus y fx. So this is the value of the torque by comparing these two equations. And if I write the value of the fx and fy in the component form, I will be able to get my desired result, because this is termed as the expression in polar coordinates. I'm going to write it in terms of phi. Now this is the same diagram as the previous diagram. This is point P only. But the thing is that all the point Q and other things are not shown because that is not the requirement. So, but in this diagram, I have drawn the perpendicular. This ON is drawn perpendicular on the line of the force. This is, of course, y-axis is taken as the axis of rotation. I can again show d theta and all that. This diagram, again, r is the position vector with you, and theta is the same angle as the previous diagram. This angle is alpha for the force with the x-axis. So I can write the component of the force in the along the x-axis. It will be f cos alpha, fx will be equals to f cos alpha, fy will be equals to f sin alpha. And the value of x is r cos theta, value of y is r sin theta. Now you can put these values, you can rearrange the things, and on rearranging you are getting torque, it is equals to rf, I have taken out. Inside I am getting sin alpha cos theta minus cos alpha sin theta. So this is the formula in trigonometry. You can write it as sin of alpha minus theta. So I want to take the value of this alpha minus theta. So you have to refer to this diagram. If I say this angle is alpha, then if this triangle OP, you may name it something like R. If I name, if I take this triangle OPR, then the exterior angle has to be equals to the sum of the opposite both the interior angles. So this angle at P point, which is there, that I am terming it as phi angle, which is of course the angle between the direction of the R, this is your position vector, R vector, and the direction of the force. This line, if I extend, this is the direction of the position vector, and this is phi. Phi is the angle between the direction of R and F. So if I'm taking this phi is the angle between R and F. And from this diagram, you can say that alpha, it is equals to theta plus phi. These both the angles equal and opposite. If this is phi, this has to be phi. So you can write theta plus phi, it is equals to alpha. From there, you can find the value of alpha minus theta, that comes equals to phi. So phi, it is equals to alpha minus theta. So if you put this value of alpha minus theta here, I am getting RF sin phi. Or I can simply write f into r sin phi, and from here you can see the diagram. Phi is this angle So sine of phi is this perpendicular ON divided by R. Sine phi, if you want to write, that is equals to ON divided by R. So ON can be written as R sine phi. If you wish to write, you may write here. Sine phi, you can write the value for sine phi, that is equals to, here's ON, it means D divided by, here's this vector, R vector. So D can be written as R sine phi. So I can write this formula as F into D. So this D is the perpendicular distance ON from this diagram, you can see. And otherwise, from the knowledge of the cross product of the vectors, you can see that your RF sine phi, it means I can write it as R cross F. So R cross F, you can write it as the value of torque. And you can find the direction R vector, this hand, and you turn it along the direction of F vector. R, you are keeping the finger along the R direction, you are turning it along the F direction. Then the direction in which thumb points, like for this diagram, it is pointing towards me. So the torque is acting perpendicular to the XY plane and towards me, it means inside. So that way you can find the direction of the torque which is perpendicular to R and F vectors with you. And so direction finding is by the right hand thumb rule. And of course, special cases you can see if phi is 0 or 180 at this angle. It means I'm applying this, just beta this diagram has to be clear with you. If this phi is 0, it means my force is acting along this direction only. Clear? So that this direction, if I take, this means if I want to write the direction of this force I want to divide further, this also can be asked is the question that this is your, if along this direction I want to resolve force, then this is the radial component Fr. This I may term it as the transverse component Ft. And you can see that it is only the transverse component, sine phi component, which is producing the torque, and the radial component has nothing to do. It means if phi is 0, I'm pulling this scale along the R vector. This is R vector. I'm not applying force at an angle. I'm pulling it along the same direction. Then it is not going to produce any torque. So this radial component of the force is not going to produce any torque. It is only the transverse component which is producing the torque. That is R sine phi is producing the torque. So if this phi is 0, then it means torque will be 0. Even if I apply, means I pull it, otherwise means I'm applying the force at 180 degree in place of pull. If I push, then phi is 180, then also the torque will be 0. So torque is going to be maximum only when theta is 90 degree. It means you are applying the force perpendicular, and of course this maximum value will be further maximum. I can say that torque has to be maximum when theta is 90 and when the value of R is the greatest. It means you are, that is the reason why handles are provided at the edges, just to increase the value of this R. I am able to write this work done in terms of torque into d theta. So if I divide, or I divide by the small interval of time, dt or delta t, then I am able to get the formula for power in rotational motion, that is rate of change of doing work, power, that is given by torque into omega, because d theta by dt is the angular velocity. So this is again a relation with you for the power in rotational motion when we talk. It is given by torque. New term with you which you are using otherwise in day-to-day life many times, that a couple, when we talk about a couple, like you are using this couple to open the cap of this bottle, I'm applying the force by two fingers. It is not easy to open it with single finger. So both the finger, like simply you open the cap of your pen, then also you are applying the couple. So two equal and opposite forces are to be applied. These forces, different forces, they are acting along the different line of. Like if I'm taken this diagram with you, this one force F is acting in this direction, the another force is acting in this direction, but magnitude is same, then that constitutes a couple. Means a pair of equal and opposite forces acting on a body along two different lines of action. So for this, if you see the distance OA, this distance for this force, if I'm saying I'm applying at this along this point, O is the point, then I can write the torque which is given by F into OA is the perpendicular distance for this first force, and for this force which is at B, the perpendicular distance is OB, and OA and OB is taken as a small d. So it means it is independent of the choice of the O point. Lever point can be anywhere, but this torque, which is moment of the torque or the couple, I can say here, that is given by F into the perpendicular distance between both the lines of action. So for this couple to produce, both should be having the equal and opposite forces. Means again that is a repetition. I can say that if I want to write the torque in the component form, I can write it as I cap tau x plus j cap tau y plus k cap tau z. For R, I can write x I cap plus y j cap plus z k cap. For F force, I can write Fx I cap plus Fy j cap plus Fz k cap. So taking cross product, you all are aware, you have to write it in the form of this matrix Ijk of case plus minus plus. And then you can write the value for the multiples of I cap, which is simply by omitting this line and this line horizontally and vertically, I am getting I cap into y fz minus z fy. Minus of j cap, I will be eliminating this line. I will be eliminating this line of case. Then I am left with x fz minus z fx. Similarly, for getting the product of this k cap, I will be eliminating this line of k. So I am getting x fy minus y fx. So from here also you can see this I got the result when I derived in the Cartesian components. So this is the z component of the torque. It means if I am moving the body in xy plane, torque is acting along z axis. So on comparison, you can compare the components I cap, j cap and k cap components, and then you are getting the value of tau x, which is equals to y fz minus z fy, and for tau y you are getting z fx minus x fz. For tau z you are getting x fy minus y fx. So this last result we have already derived. So you should be able to write the torque in the component form. And for the body to rigid body to be in equilibrium, it should be having the translational equilibrium. It means translational equilibrium means force external should be equals to 0. It means force along the x-axis, y-axis, z-axis should be 0, or I can say velocity for the center of mass. For this of course we can take the stable equilibrium, unstable equilibrium, they all come under the years translational equilibrium. So this is simply I am drawing an example to explain you the thing. So if I take a cone and I put it in this way on the means stable equilibrium, then if I'm stable equilibrium means body is, if I apply small force at any edge, it will change its position for a second and then it will come back to that position. It will not go anywhere. Of Okay, center of mass will be little raised. Potential energy is minimum for stable equilibrium. For unstable equilibrium, if you apply a small force, then it will never regain its position back. For neutral equilibrium, center of mass remains same at all, means while disturbing the system also, no change in the potential energy, no change in the center of mass. But for this stable equilibrium, potential energy has to be minimum. Unstable equilibrium, if you apply the force, it will go down, means it will never regain its position, and of course potential energy will be. When we talk about the rotational equilibrium, then torque external should be equals to 0. It means R cross F should be equal to 0. This is the condition for a rigid body to be in equilibrium. And when the body is in equilibrium, as this principle we have used in the physical balance for measuring the gravitational mass. This is fulcrum. You have played in the park also, that you sit on one side of this seesaw, and you just your friend is on the lower side, and then you raise up otherwise. So this way, this is fulcrum yours. And for this system to be in equilibrium, your anti-clockwise movement, anti-clockwise means this way, whatever movement is there, that should be equals to the clockwise movement for the second force. So anti-clockwise movement should be equals to clockwise movement. That movement, that is force into perpendicular distance. Perpendicular distances are taken d1 and d2. So w1 into d1, that is equals to w2 into d2. It means this relation need to be true for the principle of movement, and this is known as your lever principle. So you people are supposed to keep things up to this. Of course, we can continue in the next class. So thank you everyone.